To the May FPGA seminar. So we've got two talks today. We'll start off with one from Bill and Jason.
Yep, thank you, Paul. Today I'll be talking about latch-based performance optimization FPGAs. Jason and I submitted this to FPL, and hopefully we'll be hearing from them soon. So the first question we have is, why do you want to use Why do you want to use latches? And the reason why we want to do so is because the fact that the reprogrammability of FPGAs has a performance penalty. In fact, it's around 3 to 4x slower based on a study done here at the U of T by Dr. Kwan. So we need to somehow close this gap between ASICs and FPGAs. And so one of the ways that has been studied so far, at least, is how to use clock skew and latch-based optimizations. These are used in today's high-end microprocessor designs, and they help. There's one reason why it helps us, or helps these designs reach, for example, 3 gigahertz. And what also helps is the fact that commercial FPGAs, such as Xilinx, already allow us to configure any edge-triggered flip-flop to be a latch. And also, we can generate clocks with different duty cycles and different phases. I'll go into detail about both of these points a bit later on. But the goal of the work is to somehow improve the performance of current designs without a power or a hardware penalty. And so here's an outline of my talk. I will go over standard timing analysis. I'll do a brief review of clock skew, as well as latches. I will then talk about how pulse latches can help us solve this timing optimization problem. And I'll detail the advantages and our approach. And I will talk about the results and then conclude the talk with the ongoing and future work. So this is standard design, or a very simple design. And for us to figure out the clock period we can clock the circuit at, it is simply the longest path between any two flip-flops. And that is 8 nanoseconds between the leftmost flip-flop and the middle flip-flop. So then the question is, well, how can clock skew help? Clock skew can allow us to intentionally delay the clocks feeding into any of the flip-flops. So in this case, if we put a 2 nanosecond delay on the second flip-flop, we see that we can clock this circuit at 6 nanoseconds because we're essentially stealing 2 nanoseconds from the second stage for the first stage. Oh, by the way, this is also known as time boring or cycle stealing, and I'll use these terms interchangeably in the rest of the presentation. And so let's take a look at a time diagram of this of clock skew. So we see that without clock skew, the signal from the first flip-flop to the second flip-flop arrives too late. And if we do add the 2 nanosecond delay to the second flip-flop, it can arrive on time. But with this delay, or this shift in the clock feeding the second flip-flop, there is a potential problem here where the signal can launch from the first flip-flop and get to the second flip-flop before the edge occurs. And this would violate the original behavior of the circuit, and hence this is known as a hold time violation. So then the question is how can we actually implement these skews? One way that Dr. Singh here at the University, or at the University of Toronto, tried was to basically generate multiple clocks phase shifted from each other and then deliver them across the chip. The skew set was determined automatically for each circuit, and he found that with only 4 clocks, you can achieve 20% improvement in circuit speed. However, these extra clock lines has a power overhead associated with them. So another thing that has been tried by Professor Guy Lemieux's group at UBC is to attach a programmable delay element in front of every single flip-flop and adjust these PDEs accordingly so that we can reduce glitch power and improve the circuit speed using clock skew. He showed that this gave a 15% improvement in circuit speed, but this requires architectural modifications. And so, before I talk about how we use latches, I'll first give a brief overview as to how a latch works. So, we know that when the clock is active, Q essentially tracks D. And when the clock is not, we see that Q does not react when D changes. So essentially, Q tracks D when the clock is active. So let's go over a simple timing analysis example. So the difference here is that what we've done is we've replaced the second sequential element in the middle as a latch, but the other two are flip-flops. And so if we use a clock period of 6 nanoseconds, let's see how this circuit will behave. So the signal will arrive from the first flip-flop at the second latch when the clock is high. And because the latch is transparent when the clock is high, it can pass straight through, arriving at flip-flop 3 on time. So, but what if we, oh, that's a little hard to see. Well, okay, what I'm trying to show here is what happens if we have a 3 nanosecond delay between flip-flop 1 and latch 2, and a 3 nanosecond delay from the second latch to the third flip-flop. And so if on the second cycle, this signal gets launched from the flip-flop 1, it'll arrive at the second latch when it's still transparent, and it'll pass straight through to flip-flop 3, arriving when the original signal arrives. And we essentially have two signals arriving at the same flip-flop at the same time, and that's undefined behavior. We can't allow this to happen. And so one solution is to use pulse latches. So the signal passes through the second latch as before, but when the second signal launches, it arrives when the clock is not active. And so it has to wait until the next cycle before it can proceed, just like in the standard flip-flop case. So one of the other advantages for using latches is that latches can mimic multiple skews or multiple different phases with just one clock. So because of the fact that it can be transparent. So these are just examples of signal paths that can start at a latch, go through a latch, and then potentially keep going through a latch when it is transparent, and just keep going. And this is analogous to the fact that you only sort of steal from your neighbor whatever necessary. You don't steal more than what you need. But this is not true if you use clock skew with flip-flops. And another reason why pulse latches is this thing we decided to try is because modern FPGAs already have the functionality for us to configure an edge-triggered flip-flop to be a latch. On the right here is a screenshot of the Xilinx FPGA editor showing a sequential allowing it to be configured as a flip-flop or a latch. As well, there is already dedicated circuitry that allow us to synthesize clocks with different duty cycles. So the basic approach of what we tried is, given a routed design with only flip-flops, we would like to selectively replace some of the flip-flops with latches and choose a duty cycle for the design such that no hold time violations occur. And currently we're only working on single clock designs. And so the first, there's a couple of stages to our approach. The first stage requires us to calculate the optimal clock period for a given circuit. Now, suppose that we ignore hold time violations for now, and we just consider setup time constraints. And so what we can do is construct a graph, like so, where each vertex in the graph represents a register. And edges between vertices represent delays on combinational paths between registers. So if we look at this circuit without concerning any time borrowing, any cycle stealing, the best we can clock this circuit at is 10 nanoseconds because of the path from A to D. Now, if we can cycle steal, what we can do is we see that this cycle is the cycle that constrains the best possible frequency we can clock the circuit at in a valid fashion. And we can clock it at 6 nanoseconds, and the best way to think about this is if you sum up the delays around the cycle and divide it by the number of stages the cycle spans, you essentially get a cycle called the maximum mean cycle. It can be proven that the maximum mean cycle gives you the optimal clock period for any given circuit. Instead of me trying to formally prove it to you, let's go through some of the other cycles present in the graph. So the maximum mean cycle algorithm also gives us the different time borrowing amounts necessary to implement the given clock period. So in this case, we see that we need to borrow 4 time units for D, and it's a lot hard to see, but we also need to borrow 1 time unit for C for every signal to arrive on time. But let's look at another cycle. So this cycle spans all 4 vertices, and if we try to calculate the cycle mean, its value is 6 plus 4 plus 3 plus 5, which is 18. And this spans 4 stages, 4 combinational stages. And this would give us a clock period of 4.5 nanoseconds if we choose so. But we see that 4.5 nanoseconds does not work for the cycle going from A to D to C and back to A. Because if you try to do so, you essentially try to borrow from your neighbor, and your neighbor try to borrow from another neighbor, and eventually you'll come back to yourself, meaning that you'll have a cycle of infinite time borrowing, and that's obviously impossible. And so what I tried to show you here essentially is that the maximum mean cycle does give you the optimal clock period. And so in the previous example, I only showed you the graph with setup time constraints or long path constraints. Now let's talk about how we can actually incorporate hold time violations or hold time constraints into our formulation, because no circuit can work without considering these. So on the far left, top left, we see that suppose we had a signal that takes 1 nanosecond or 1 time unit terminating at A. On the right, we have a timing diagram showing that without it shows that basically we can allow up to a pulse width or amount of 1 nanosecond time borrowing before a hold time violation occurs. If this edge goes any further, which means that we borrow more than 1 nanosecond, this signal will have a hold time violation. So we can conclude as of right now that we can use a pulse width of 1 nanosecond safely. But the question is do we even need to borrow time for vertex A? Based on the maximum mean cycle calculation and the associated amounts of time borrowing, we see that A does not actually require to borrow time. So in fact, we can just leave it as a flip-flop for now, but we will actually make the final decision later. So there's a second case that I want to go over. Suppose we had a signal terminating at C that takes 2 nanoseconds or 2 time units. The right is, again, the timing diagram, and we can say that we can use up to 2 nanoseconds of time borrowing for C before we get a timing violation. The thing that differs between C and the previous case is that C, based on the maximum mean cycle calculation, requires borrowing 1 time unit, as shown in the top right of the graph. But that is still less than 2. So that does not produce a hold time violation. And so what we're going to do is sort of proceed in a greedy manner that tries to maximize the amount of pulse, maximize the pulse width. Since this does not cause a hold time violation, we'll proceed further. So this is the third case, down at the bottom right corner of the graph. So the signal arriving in D takes 3 nanoseconds, but the max mean cycle calculation says we need to borrow 4 time units for us to implement a clock period of 6 nanoseconds. Based on that timing diagram on the right, you can clearly see that that, left on its own, is a hold time violation. And so for us to fix this, we have to use a pulse width of 3 nanoseconds, basically bringing this edge to where the signal arrives at, essentially. So if we make this assumption and assume that we're going to use a 3 nanosecond pulse width for the whole circuit, since our goal is to use 1 clock for the whole design, we note that 3 nanoseconds would cause a hold time violation at A and C because both of the terminating signals are less than 3. So what we have to do is convert A and C both to flip-flops, meaning that we constrain them to borrow no time at all. And also we have to constrain D to borrow only 3 time units. So if we add these modifications and we try to resolve for the optimal clock period, we can quickly see that A to D is still the limiting edge, but it can only borrow 3 nanoseconds or 3 time units from D now, yielding an optimal, yielding a clock period of 7 time units. And so let me just summarize what we just talked about so far. So we're going to compute the optimal clock period without considering any hold times. We're going to compute all of the minimum delay paths between every pair of registers. There's basically n squared paths between them, between every, at most n squared number of paths. And we will sort the minimum delay paths in ascending order, iterate over the paths until we reach a situation where a signal arrives at a register that requires more time borrowing than the actual signal duration. Set the pulse width so that this is not a timing violation. And then force sequential elements that have that receive signals shorter than the pulse width to be flip-flops, because they would themselves introduce timing violations if left unchecked. And then finally, with these new constraints, we'll calculate the clock period. So to run our experiments, we ran it in the VPR 5.0 framework. Our performance optimization was built with the aid of the C++ Boost library. And we used 27 academic circuits, all of the sequential MC, NC circuits, and all of the VPR 5.0 circuits, I believe. And just to stress, this optimization was done after place and route. So one of the key challenges for our trying to figure out how we can accurately measure the benefits of our optimization is that VPR does not model any minimum delays. It only models the long path constraints. So what we did was we computed the minimum delays between every pair of registers, and then for each delay, we took a fraction of that computed delay. And then we considered 3 different scenarios, 60% pessimistic, 70% nominal, and finally 80% optimistic. So here are the results of our experiments. So the first thing to note is that we normalized the clock periods to the standard flip-flop case, i.e. the critical path on the far left. And everything else is measured accordingly. Each of these results are averaged over across 27 benchmarks, as mentioned before. I left out the 80% case, as you notice, because they're essentially the same as the 70% case. For 70%, we see that pulse latches gives a 5% improvement, whereas the clock skew case, when we assume we can use as many clocks as possible, essentially the optimal clock skew case, can only give 10%. Now both of these measurements are done in accordance to hold time constraints. However, the thing to note is that for 60%, we only can get essentially 2% improvement in circuit speed, whereas clock skew does not really change. Finally, one thing to note is that the optimal clock period we can clock the circuit at, on average, is 29% better than the critical path delay with just conventional flip-flops. So that just shows you that we still have a long way to go if we are trying to achieve the optimal. So what is limiting our gains from achieving clock skew? It's essentially achieving the same results as clock skew or achieving the optimal results. Well, first off, we have these essentially structures called self-loops, essentially paths that start and end at the same latch. Now, what makes this peculiar is that this case only affects latches because of the fact that it is transparent. And so you can think of if a path starts from a latch and then comes back before the transparency period is over, that is a hold time violation. Another case that affects clock skew and pulse latches are the extremely short intra-CLB paths between registers. And currently VPR models them as a constant delay. And finally, the CLB is modeled as fully connected, meaning that you can go from any logic block to any other logic block within constant delay. Now, we do not believe that this is an accurate representation of commercial FPGAs, and so if this was not the case, we would be able to reduce the frequency of the number of short path in intra-CLB connections. And so how can we fix these problems? So the most obvious way is to make some connections longer by taking more circuitous routes, or bring the intra-CLB connections outside and let the router route the connection. As well, we can integrate the notion of latches into placement and routing, as well as clustering, by essentially changing the criticality metrics, meaning that we change how we want the tools to optimize the design. And what we essentially want to do is to optimize the critical cycle rather than the critical path, at least for timing. So in summary, modern FPGAs already provide us the capabilities to implement or use pulse latches. I showed that in the results that much of the benefit of using many skewed clocks can be achieved by using a single clock with pulse latches. In under 70% minimum delay assumptions, we can achieve a 5% improvement in speed, essentially free of power or area overhead. That concludes my talk. Any questions?
So you're just assuming the baseline Xilinx hardware, and how would you generate the pulses for that?
Well, I believe that Xilinx already provide. They have like I think it's called the DCM, and it says they can generate pulses of 1 to 99% duty cycles. Mm-hmm. But I still have to take that as a grain of salt. But they say they advertise it as so.
So you're just assuming you can generate.
Yeah, I'm assuming.
Pulses,
Yeah.
You're kind of sweeping jitter and
clock
skew all under the rug.
Yeah. So this is sort of like more of a theoretical approach as to how we can possibly attack the problem. But yeah. Arun?
So the other question that I had was, you're making the assumption that after you place and router the design, you can selectively target flip-flops and turn them into latches.
Right.
That's actually not true, because if within a CLB, you can't select individual flip-flops and turn them into latches.
Okay.
The other thing to keep in mind is that from vertex 6 onwards, only half of the flip-flops can be turned into latches, the rest of them can only stay as flip-flops.
Okay, I did not know that, but that's an interesting thing. So basically, inside one CLB, you can only turn at most half of them to latches. Is that what you're trying to say, or?
So, in a vertex 5, or
Okay,
in the previous, all the flip-flops can only be configured as either all flip-flops or all
Okay.
latches.
Okay,
Right, so you can't target one in there and say,
Okay.
oh, this is a latch, this is a flip-flop.
right.
The other thing to keep in mind is that in a V6 forward, so you still have those 4 flip-flops that can either be flip-flops or latches,
Mm-hmm.
but then there's 4 more within a slice, and those are only ever flip-flops.
Okay.
Sorry, CLB.
Okay, that's interesting. Yeah, we did not. We cannot find anything that stated that, but yeah, it's hard to find latch documentation in the first place. Yeah, go ahead.
The other thing I was going to ask about was modeling, like, or looking at designs with more than one clock.
Right.
And addressing the fact that you have a limited number of clock networks in the design or
Right.
device.
Right.
And those restrictions will affect how well you can actually bring all these clocks together into various.
Yeah, that's right. Yeah, the problem is that VPR is done only in the single clock scenario, and so for us to sort of even, I think for us even to test it, we need to have EPR support multiple clocks.
Yeah, no, I recognize it's
yeah.
a problem, but
Yeah.
it's a limitation to.
Yeah, that's definitely true. Yeah, we sort of did this in the context that we assume that the circuits are all single clock, and then we said, okay, well, can we still use a single clock and get something out of it? So.
He's not generating extra clocks, though. He still is sticking with single clock. Just choose a duty cycle for it and choose some storage elements to be latches, so he's not generating extra.
Okay,
But one
so-
approach is
Oh.
you could run multiple extra clocks with different duty cycles, and you push the right duty cycle to the right storage element for it.
Okay, but
That is
so
a
there's
distinction.
just not going to be one clock in the design.
Yeah. So on our experiments, we basically said we're going to pick one clock with a specific pulse width, and then use that pulse width throughout the whole design.
Okay.
Yeah. So that's what we are trying to attack.
But what you said, Bill, you have thought of that, having multiple clocks with different pulse widths.
Yeah,
It's a
that's
good
right.
idea.
Any other questions?
So,
Like,
so
yeah.
what about, so maybe Dave might ask, like in terms of process variations, you know, how much variability do you get in a delay path?
Well, you get lots. You have VDD, you've got process, and local variation, so it's huge. Probably more than 2 to 1, but it's also correlated. So if you're, in this case, you're generating, 2 clocks are probably going down similar paths, and they've got roughly similar process corners and similar VDDs and stuff, so you can take advantage of correlation.
Okay, thank you, Steve.